Okay, so we will continue first this problem on angular momentum. If you remember, we had a sprinkler that is rotating at a constant angular velocity omega, and we demonstrated that for the control volume we considered, we don't have a transient term. And we still have to compute the angular momentum fluxes crossing the control surface. So we have at the inlet, we mentioned that we have, since for the inlet line will be along this direction, along OA, so it will not be able to produce any moment about O. Okay, so the angular momentum of the inlet is 0. So we just have the angular momentum at the out. Okay, because if you remember, if we go back to the figure of the system, the flow is coming. So you have the flow is coming from here. So if we look at this figure, this is the inlet. So since M times V inlet is along the axis of rotation, so it cannot produce any angular momentum about it. Okay, so we just have the fluxes crossing out the control surface. So we have two outlets here, and we should account for both. Okay, so we should find the angular momentum of the linear momentum al outlet. Okay, so to do this, we should find first the expression of the velocity vector. And you know that in order to find at the end the angular momentum, we do R vectorial MV. Okay, so now first let us go back to the figure to see how to express the outlet velocity. Okay, this is the outlet velocity. If you remember, this outlet velocity is doing an angle of 30 degrees with this line, with this direction. Okay, and therefore I can decompose the outlet velocity into different components, into I, J, and K components. So first, the component along the axis is just equal to V relative, which we calculated together from conservation of mass. Okay, so you have, this is your Z component, okay, which is equal to V relative sine 30. Now you still have to find what are the components of the outlet relative velocity in XY plane. Okay, to do so, first you project this velocity along the horizontal plane. This projection here is equal to V relative cosine alpha, and alpha is 30, so it's V relative cosine 30. Okay, now this line, this segment here, should be decomposed into X and Y. So if you plot XY axis at this level, okay, you have that this line, I will draw it here for you. This line is perpendicular to rod OA. Okay, so this is perpendicular to OA. And since OA is doing with x-axis an angle of theta, so this line is doing with x an angle of 90 minus theta. And therefore, I can say that the projection of the velocity, so here, this is the velocity projection on the horizontal plane, okay, equal to V relative cosine 30. I can decompose it into positive x component and negative y component, okay? And the positive x component will be equal to this length, which is V relative cosine 30, times cosine 90 minus theta, or times sine theta. While for the vector if you want for the vector component along y, it's a negative component. So I should put minus v relative cosine 30 and then multiply by cosine of theta. Okay? So now, once I do this, now I am ready to replace in my equation. What is my purpose? My purpose is to get the fluxes of angular momentum crossing my control surface. So I should do, okay, I should do the following. So after getting my V relative, this is how we get it here, okay? You get the expression of V relative. So V relative, as we said, is decomposed into three components. One along I, which is V relative cosine alpha sine theta. One along J, which is a negative component, minus J V relative cosine alpha cosine theta. And along K is plus V relative sine alpha K. So these three terms stands for V relative. Okay, they will represent the relative velocity exiting the control volume. Now, remember that our control volume is fixed, okay? And all velocity involved in the angular momentum relation are absolute velocities. This is why we should compute the total velocity of the jet. To do this, we should add to V relative, okay? We should add the velocity at the tip, okay? We should add the tip velocity. So what we will do now is that we will go back, we'll go back to the figure to calculate what is the velocity at the tip, okay? If you look at the figure here, we consider that since this length here, L, is not given, we consider that it's a pretty small length, L, so that we can consider that the velocity of rotation at B is equal to the velocity of rotation at A, okay? So to get V total at the exit, we should add the relative velocity, which we calculated now. We should add to it the velocity of rotation. So I have V relative plus V rotation. Okay. Now, what is the velocity of rotation? You have your system is turning at an angular velocity omega. You know that in rotation, the velocity of rotation at a certain point is always tangent to the circle, okay? So here, the velocity of rotation will be perpendicular to OA, and in magnitude will be equal to what? Will be equal to omega times R. The radius is OA, okay? So it's omega times OA in magnitude. Now we will decompose it into IJ components. So as you can see, this velocity is perpendicular to OA. So if I want to draw it here so that you can see the components, okay, along X and Y. So this is my velocity. This is my velocity V. Okay, it's perpendicular to the arm. And since you have that the arm is doing with X an angle theta, so this velocity will do with X an angle of 90 minus theta. And if you do projections, you have negative velocity along X and you have positive velocity along Y. So the projection along Y will be omega R or omega OA cosine theta, while the projection on X will be minus omega R sine theta. Okay, so now we are done with the expression of the total velocity at the exit. So we'll be able to calculate the angular momentum. Okay, so now all we have to do then is to compute what is R vectorial V. Okay, so as you can see here, velocity of the tip, as we said, has a negative component along X and positive component along Y. and now we add it to V relative to find the total velocity. Once I find the total velocity expression, I should compute R vectorial V at the outlet. Okay, so we know, as I told you, the outlet is at point B, so I should do RB vectorial VG. But since they didn't give me the length of the small part, I will consider B and A as one point. So RB is equivalent to R of A. So R of the jet at the exit is equal to R at A. And R at A, I can simply find it by going back to this figure. This is R of A. It's the position vector from O to A. I will decompose it into two components. One along I, which is a positive component, is equal to plus OA cosine theta along I, and along J, it's plus OA sine theta. Okay, so now I have all my vectors required to compute R vectorial V. So now all I have to do is to do the vectorial product, RB vectorial VG. And remember, always in the vectorial product, you can use, if you have a right-handed coordinate system, you can use the following circle, IJK. So if you have I vectorial J, it will give you plus K. So just you have to look at this circle in the positive direction. The positive direction is from I to J to K. If I tell you K vectorial J, so I'm turning in the negative direction, will give you minus I. So let us try here. For example, all you have to do is to expand term by term. So you start by IR cosine theta vectorial this term, okay? But you know that I vectorial I is 0. So this term will cancel out. Then you move to the second term. You have I vectorial J. I vectorial J, if you turn here in the positive, you are turning in the positive direction from I to J, it will give you plus K. But already you have a minus before J, so this is minus K times this result. Okay, so you do R cosine theta times V relative cosine alpha minus omega R cosine theta times minus K. And you continue to expand term by term, okay? And when you are done, you group I terms together and J terms together and K terms together. You end up with the following result after some simplification. Because, for example, along K, you will get V relative cosine alpha minus omega R times sine square plus cosine square. And this can be replaced by 1. Okay? So now this is your result for R vectorial V. Okay? Now don't forget that you have two outlets, not only one. This is why we should add not only R vectorial V at the first outlet, we should add also what is R vectorial V for the second outlet. But why we can deduce R vectorial V of the second outlet from the first one? Because if you go back to your figure, look at your figure. This is the relation between the first outlet and the second one is that the difference between R of the first, okay? So R of the first is at a certain angle theta, while for the second arm, the angle will be, this is the total angle. It is pi plus theta. So no need to repeat everything. You can keep the same expression, just you will replace into your result theta by pi plus theta to get what is R vectorial V at the second outlet. Okay, so what we will do is that by looking at this expression, okay, you have that all we have to do is to replace in this result here to get, so this is for the first exit. This is the result of R vectorial V for the first exit. For the second one, all we have to do is to replace alpha is the same, it's 30 degrees, but instead of theta, it's pi plus theta, okay? It's pi plus theta. And this will simplify a lot, you know why? Because when you will add both, okay, you have sine theta is minus sine pi plus theta. And also cosine theta is minus cosine pi plus theta. So this term, when you do the addition, these terms will cancel out. And you will only have 2 times this term, okay? Yalla, we'll see this in the final expression. So now, whenever you are done with this, you know that to calculate the total flux of angular momentum over your control surface, you should do integral over the control surface of r vectorial Vg times rho v dot dA. This represents the mass flow rate m dot. Okay? Since here we have constant velocity al outlet, so we can just say that this term, okay, so for each jet I should compute this term, okay? So this is the integral for the first exit, okay? So this is for the first exit. For the first exit, I replace r vectorial v by the result I got, function of theta and alpha. And since m dot is the velocity is uniform across the area, then I can multiply this by m dot at exit 1. And m dot at exit 1 is half m dot total, okay? Which is rho q over 2. Now, for the second exit, I have to repeat the same procedure, but now instead of replacing by theta here the angle, I will put pi plus theta. And when I do this, okay, when I do this, these terms will cancel out, because as we said, cosine pi plus theta is equal to minus cosine theta, and sine theta plus pi is equal to minus sine theta. So when I do the addition for both terms, okay, I will get double the double of this term. So I will get minus k r times v relative cosine alpha minus omega r times rho q. And now I am done, okay? All I have to do, my purpose, you know, if you remember what was the question, my purpose was to get the torque, the friction torque, okay? And to get the friction torque, I applied the angular momentum law. And this law will tell me that sum of couples acting on my system, and here, the only couple is the friction couple. The friction couple will be opposing rotation. This friction couple, okay, is equal to the transient term, which was demonstrated to be 0, plus the fluxes of angular momentum crossing the control surface. So now, since I have computed all terms, all I have to do is to put the equality that the friction torque is equal to the total angular momentum flux crossing the control surface. And this will give me what is the expression of the friction torque. This is a complex, very complex problem, but please try to repeat it, because it will allow you to well understand the concept of angular momentum, okay? And I will do with you now some additional practice problem on angular momentum so that you can know how to do the method in a better way, okay? Any question on this problem before I start with other problems? So already I posted for you problems on the different conservation laws, continuity equation, and linear momentum equation, okay? And now we'll do problems on the case of angular momentum. So let us consider the following problem first. Water at 20 degrees flows at 30 gal per minute through the 0.75-inch diameter double pipe band of the figure. The pressures are given, so we have the pressure at section 1. We know the value of P1. We know the value of the pressure at section 2, P2. And what we want to know is what should be the torque T that should be applied at B, okay, in order to keep the pipe from rotating. So we don't want our pipe to rotate, okay? This is why we need to put a certain torque. This torque should balance, if you want, angular momentum fluxes على control surface, okay? طيب, how to proceed in such problem? First, since they are asking for a torque, you should think about the angular momentum law, okay? Now, of course, here it's clear what should be my control volume. I will take my control volume, the whole system, and I will draw the free body diagram of forces, okay? I have the atmospheric pressure is acting everywhere, so it will cancel out. I will just have the values of pressures P1 and P2, okay? So I have P1 applied at section 1, P2 applied at section 2, the values are given, plus I have the torque that should be applied at B, okay, to keep my system from rotating. So I am in steady conditions, okay, no transient term. So if I write the angular momentum relation, I will say that summation of couples of forces, and you should consider couples and moment of forces. So summation of moments, including couple and forces moments, should be equal to integral over the control surface of R vectorial V. Here, it's much simpler. Here in this problem, you will see that it's easy to find, and no need to do vectorial product. Sometimes vectorial product, like in the previous example, is required when you have 3D applications. But in 2D application, you will see that it's very easy to calculate R vectorial. Okay, so R vectorial V times rho V dot N dA. In such a problem, the integral procedure is simple because you have uniform velocity على inlet والoutlet. So this term, because you have uniform velocity, this term will give you m dot, okay, when you integrate. So that you can just say it's R vectorial. So you have for inlets minus R vectorial V inlet times m dot inlet. Okay, and for outlets it's plus. So plus, of course, this is R على inlet plus R outlet vectorial V out m dot out. Times m dot out. Okay, so now if you look at your problem first, you should calculate m dot in and m dot out. It's very simple because they gave you the flow rate. Okay, gal per minute, you can convert it easily to feet cube per second. Okay, so you have the conversion factor, you can find the expression of Q, and knowing the value of rho for water, you can get the mass flow rate. So this is m dot in slug per second, okay, in English system. Now, you know that from continuity, because of steady operation, we have m dot in is equal to m dot out. So already we are done with the calculation of the mass flow rates. And now we need to compute what are the velocities at the inlet and outlet. All we have to do then is to say that V1 is equal, since you have same cross section, So A1 is equal to A2. And since it's an incompressible flow, then V1 will be equal to V2, will be equal to Q over A. And since here you have a piping system of circular cross-section, so the area is simply pi d square over 4. And the diameter is given. So you have it in inch. Because it's in inch, we divide here by 12 to convert to feet. Okay? And since Q is expressed in feet cube per second, so we should express the area in feet square. So by doing so, we can calculate the value of velocity in feet per second. Now, once we are done with the calculation of velocities, now we are ready to apply the angular momentum relation. Okay, so what do we have here? We have first that at the inlet, don't forget your point of interest is point B. So you will apply sum of moments about B. Since my interest point is B for the inlet, okay, the vector m dot V will not have any moment about B, since this vector is passing by B. Okay, this is why our inlet vectorial V inlet will be 0. So this term will cancel out, since this vector doesn't have a moment about V. Now, concerning the outlet flux, m dot out V out. So you have that for the outlet flux, it has a moment. And you know that how to calculate the moment in 2D. No need to do the vectorial product. The vectorial product, you can use it here, but because it's a 2D application, it's much easier to get the moment by just finding what is the distance between B and the line of action of vector m dot V. This is vector m dot V. If I do the perpendicular distance from B to this line, the distance is 3 feet, okay? And to know the direction of the moment, I just have to do the right-hand rule. So here, I have that the moment is equal in magnitude to m dot out V out times 3, which is the distance. And concerning the direction, if I do the right-hand rule, it's a counterclockwise moment. So this outlet velocity vector is tending to rotate counterclockwise about B. Okay, so the angular momentum flux is in the counterclockwise direction at the exit. Now we are ready to write our equation. Okay, what is our equation? The equation is sum of moments about B. I will consider the counterclockwise direction as positive. So sum of moments about B is equal to, please, you should pay attention first to include all torques and moment of forces. So when I say sum of moments of about B, I have the couple that should act at T, that should act at B. This is what I want to calculate. I have the moment of forces, so I should add plus moment of forces. What are the external forces acting on my system? I have, as we said, we have P1 times area. This is the pressure force at the inlet. But this force is passing by B, so it cannot produce any moment about B. The second force is the pressure force, okay, which is P2 A2. What is the moment of this pressure force? All I have to do is to multiply by this distance, H2. Okay, so, and as you can see here, this force is tending to produce a clockwise moment about B. Okay, so since I consider the counterclockwise as positive, so I should put now a minus, a negative sign for the moment of the pressure force. So it's minus P2 A2 times H2. Okay, now once I'm done with this term, I don't have any, of course you have the weight, but since they didn't give you the weight, you can consider it as negligible. Okay, so this is for the moment balance. This should be equal to what? This should be equal to del by del t, but as of the angular momentum in the control volume. So integral over the control volume of the angular momentum term. But since it's a steady application, this term will cancel out. So we just have the angular momentum of fluxes crossing surfaces. And as we said, for the inlet flux, no moment, no angle, the angular momentum will not have any moment since it's passing by B. So we only have the angular moment of the exit jet, and we already computed its value. It's equal to, as we said, to m dot out times V2 times H2, which is the distance of 3 feet. Okay, so now all you have to do is to get T is to take this term to the other side. If you take this term to the other side, you get that the torques that should be developed at B to have steady state case is equal to, you can take H2 into factor. So you get inside of your brackets P2A2 plus m dot V2. And now since you have all these parameters, you are ready to perform your calculation. So all you have to do is to replace numerically these values. Okay, and in this way you will be done. Okay, any question on this? Okay, let us consider another problem on angular momentum. The following pipe band of the figure has a diameter D1 equal to 27 centimeter, D2 equal to 13 centimeters. When water at 20 degrees flows through the pipe at 4,000 gal per minute, P1 is equal to 194 kilopascal gauge. Compute the torque required at point B to hold the band fixed. Okay. So please remember always that I should first put the three-body diagram, put all forces acting on my system to be able then to apply my conservation laws. Okay, so here my system of interest is this pipe. So this is my control volume. Now, what are the external forces acting on it? I have the pressure at section 2. And this pressure, since the jet is exiting to the atmosphere, so here they are just saying that P2 is equal to atmospherical pressure. And at P1, I am imposing a certain pressure, P1, and they gave me the gauge pressure, okay? They directly gave me the gauge because if they give me the total pressure, I should subtract from it PA. Why? Because PA is acting everywhere on your control volume, okay? So the resultant, when you perform the resultant for forces, you will just get the force due to the gauge pressure. So here at section 2, you have P gauge, P1, times P1 gauge times the area, okay? And here you can consider that since P is equal to P atmospheric, so these forces, these pressure forces, will be opposed by other from the other side, so they will cancel out, okay? So now, what we want to do is we want to compute here also what should be, what is the torque required at point B to hold the band fixed, okay? So it's similar to the previous question. We have here an inlet and an outlet. For the inlet also, I don't have any moment for the angular momentum, for the linear momentum vector. So for the linear momentum vector MV, it's passing by B, so it's not producing any moment. I just have the effect at the outlet. Okay, so this is m dot out V out. This flux has a moment about B, and I should calculate the moment of this vector m dot out V out about B. All I have to do then is to multiply by this distance. So this is my crossing flux. I have it at a distance of 50 centimeters from B. So the angular momentum will be then, the rate of angular momentum will be m dot out V out times distance of 50 centimeter, which is 0.5 meters. Okay. Now, concerning, as we said, for the inlet, we don't have any problem since it's passing by the point, so it doesn't produce any moment. Now, concerning forces, okay, we have the pressure force P1 is passing by B, so it cannot produce any moment above B. Okay. Now we should get what is the value of m dot and V2. So here also they gave us the flow rate Q. So we are able to get first the m dot by doing rho times the Q. And to get the velocities, here we should pay attention that we have different velocities. V1 and V2 are different. Why? Because we have different cross-sectional areas at 1 and 2. And since they gave us the diameters, D1 and D2, so we can calculate the velocity at section 2 by doing Q over A2. A2 is pi D2 square over 4. And A1 is pi D1 square over 4, so we get 0. So now we have all information needed. We just have to plug into the angular momentum relation. Okay. So if you substitute in your relation, as we have seen together, okay, you have that P1 doesn't have a moment about B, because as we have seen, R1 is along J, so J vectorial J will cancel out, so this term is 0. You have that the pressure P2 is 0 gauge. Since it's 0 gauge, this term will cancel out. So you just have a sum of moments about B, the couple TB, that should be applied at your system. Now, we have seen together that the inlet flux doesn't have an angular momentum about point B. So this term, because R1 and V1 are collinear, so R1 vectorial V1 will give us 0. So we end up with the result that TB is just equal to the angular momentum rate at the exit, which is m dot times R2 vectorial V2. Here they did it in vectorial method. You can do it in vectorial method, but you will end up with the same result we got together, which is just 0.5, the distance, times m dot b. Okay. Why? Because if you write vector r and vector r vectorial b, if you go to the figure, what is vector r? Vector r is the vector from point B to the exit. This is your vector of interest. Okay, this is vector r and this is vector v. But why I didn't do vectorial product here? Because it's a 2D application. So in 2D, you can directly see the moment. To get the moment, you just do m dot v times this distance. Okay. Now, if you want to do r vectorial, it's not wrong. What is your vector r? This is r. You should decompose it into I and j components. Along I, you have this distance. Along j, you have 50. Okay. And you will see that when you do the vectorial product, since the velocity vector is along I, this component will cancel out, because I vectorial I will give you 0. So just you will take into consideration the 50 centimeter component. Okay, so you will end up with 50j vectorial m dot v2 I, and j vectorial I will give you minus k. Okay, so if you go back here to this result, you will get that TB is along minus k, since when you do the expansion, I vectorial I is 0, and j vectorial I is minus k. So you can deduce that your moment TB is a clockwise moment. Okay. And if you didn't do the vectorial method, you can just look at your figure, and from the right-hand rule, you can say that the moment of vector m dot v out is clockwise. So, and since TB is equal to this couple, so TB is clockwise equal to the moment of m dot times v2 times this distance. Okay. So you are free to use any of the two methods, or the right-hand rule method, or the vectorial method to get your angular momentum. Great. Any question on this problem?